Welcome back to the deep dive. It is Friday, February 13th, 2026. And, I get what you're thinking. Friday the 13th.
Right.
Maybe just pull the covers up, avoid any black cats, and definitely don't compile any code that might, summon a demon.
Honestly, given what we're talking about today, a black cat might be the least of your problems. We're diving into the Class 9 notes for CS330.
Which means we are talking about grammar. And before you have flashbacks to middle school, I don't mean I before E except after C or anything like that.
Any chalkboards involved?
None. We're talking about the source code of source code. We're trying to figure out how we formally describe programming languages so a computer, and let's be honest, other people can actually understand them.
Yeah, this is really the foundation. We're decoding the DNA of code itself. We're going to look at the battle between syntax and semantics. We'll meet the dynamic duo of language theory.
Sounds exciting.
It is in a nerdy way. And we are going to get very, very comfortable with Backus Naur form, or BNF.
Which, if I'm reading the notes correctly, is the one tool you absolutely have to master if you want your compiler project to actually, work.
It's completely non-negotiable. If you can't define your language, you can't build it. Simple as that.
Okay, so to kick this off, the notes start with a great example. It's a simple question. Can you make me a sandwich?
Ah, the classic sandwich problem.
Right. It just sounds like a lunch order. But the notes use this to point out a huge problem in how we communicate.
It's all about that gap between structure and meaning. If you just look at the sentence itself, can you make me a sandwich? Syntactically, it's perfect.
The grammar is correct.
Flawless. You've got your verb, your subject, your objects. It follows all the rules of English.
So it passes the syntax check.
It does. But semantically, what does it mean? That's where it gets messy. Because there are two totally valid ways to interpret that structure.
Okay.
Interpretation A is, are you asking me to assemble bread and cheese for you?
The one I probably want.
Almost certainly. But interpretation B is, are you asking me to use some kind of magic to physically transform you into a sandwich?
Poof. You're a turkey club.
Exactly. Now, both of those meanings are allowed by the syntax. The structure itself is ambiguous.
And this is the whole problem, isn't it? As humans, we have context. We just know I don't want to be a sandwich. But computers are painfully literal.
They are terrible at guessing. You give a computer an ambiguous instruction, and it will either crash or do something you really didn't want it to do. And that brings us to the first big takeaway from these notes.
Which is?
It is way, way easier to formally describe syntax, the shape of the language, than it is to describe semantics, the meaning.
Why is that? I mean, why can't we just write rules for what things mean?
Because syntax is just pattern matching. Does this bracket have a closing bracket? Is that a keyword? Semantics gets into intent and logic and the state of the machine. For this part of the course, we're focused almost entirely on syntax.
So we're building the skeleton, not worrying about the soul of the machine just yet.
Exactly. We're the architects drawing the blueprints for statements, expressions, functions.
But the notes point out a pretty big catch here.
There's always a catch.
You can have perfect syntax and still write a program that's a complete disaster.
Right. Syntax checking only tells you if the program is structurally sound. It tells you nothing about whether it'll do what you want. You could write a syntactically perfect program that, divides by 0 on the very first line.
Or a perfect while true loop that just melts your CPU.
Exactly. The syntax checker looks at that and says, yep, looks good to me.
So if syntax is just the structural rules, who actually needs these formal definitions? I mean, who is sitting around reading this stuff?
The notes break it down into 3 groups. First, you have the evaluators.
The critics.
Pretty much. They're looking for flaws in a language's design. If the formal grammar is messy and ambiguous, then the language is going to be messy and ambiguous to use.
Okay, so that's the high-level view. Then there are the users.
That's us, the programmers. We need to know where the semicolon goes so the compiler doesn't yell at us, the documentation we look up. That's based on the formal syntax.
And finally, the group that you, the listener, are in right now, the implementers.
The poor souls writing the compilers. If you're building the tool, you absolutely need the blueprint. You can't write a parser if you don't have a formal definition for what an expression even is.
Okay, let's talk about that blueprint. The notes lay out 2 ways to define syntax: the language recognizer and the language generator. It feels kind of like offense versus defense.
That's a great way to put it. Let's start with the recognizer. This is what your compiler actually does. It's a filter.
Like a bouncer at a club.
Exactly. You give your source code, it checks the ID, and says either, yep, you're legal, come on in, or nope, syntax error, get out. In compiler terms, that's the parser.
But the notes say there's a problem with just using a recognizer to define a language.
There is. Imagine trying to define English by listing every possible sentence that is not correct English.
You couldn't. It's infinite. The number of ways to make a mistake is endless.
Right. You can't define a language by what it isn't. So you flip it, you look at the language generator.
Which is a system that only creates legal sentences.
Yes. It starts from a set of rules and builds valid strings of code. Now, this is the part that feels a little counterintuitive. We don't really want a computer to just spit out random, valid code.
No, a random code generator sounds like a nightmare. Here's a program. It's syntactically valid. Good luck figuring out what it does.
It would be totally useless. But, and this is the big but, the rules that a generator uses to build the code, that is the absolute best way for us as humans to understand the structure.
So we study the how to build it rules to create the how to check it tool.
Perfectly said. We study the blueprint of a good wall so we can spot a bad one.
And to write those blueprints, we needed a special tool. This brings us to the dynamic duo in the history section.
I love this story. It's like the origin story for this whole field. You've got Noam Chomsky and John Backus.
Two absolute giants. But they weren't working together, were they?
Not at all. And that's what's so cool about it. It was convergent evolution. Chomsky was a linguist trying to mathematically describe human languages. He came up with something called context-free grammars.
And at the same time, John Backus is over in the world of computers.
Right. He's working on a new language, Algol 58, and he needs a totally precise way to tell the computer what valid code looks like. He can't just be vague about it.
And they both basically invented the same idea independently.
They did. Backus made his own notation, and then later a guy named Peter Naur tweaked it a bit, and from that we got the standard, BNF, Backus-Naur form.
BNF. The notes call it a meta-language, which sounds awesome.
It's very meta. It's a language for describing another language.
Okay, so let's break down the symbols because looking at the slides, it's just a bunch of angle brackets and arrows.
It looks intimidating, but it's not so bad. The first piece is the abstraction, or a non-terminal. Those are the things in angle brackets, like a sign or an ifs meant.
So an angle bracket thing is basically a placeholder, a variable for a piece of grammar.
Exactly. It means this needs to be defined further. The opposite of that is a terminal. That's the actual code. The word if, an equal sign, a plus sign. They're the endpoints.
And the rule connects them. The left-hand side is the thing you're defining, like a sign, then an arrow, and the right-hand side is the definition.
Right. And there's one more super important symbol, the pipe. A-te. It just means or. So a rule like var ABC just means a variable can be an A, or B, or RTC.
Simple. But then the notes introduce the recursion trick, and this is where my brain started to bend a little. This seems to be where all the power is.
This is the superpower of BNF. Think about it. How do you define a list of identifiers? Like int XYZ. It could have one item or 100.
Right. You can't have a rule for one item and another rule for 2 items and another for 3. You'd need infinite rules.
You can't. So you use recursion. You define the list in terms of itself.
Okay, can you walk us through the identlist example from the slides? I think hearing it makes it click.
Sure. The rule is basically identlist, identifier, identifier, identlist.
Okay, let me try to break that down. The first part, before the or, says a list can be just a single identifier. That's your base case, your stopping point.
Correct. If you just see X, you're done. That's a valid list.
And the second part says OR, a list can be an identifier, followed by a comma, followed by another identlist.
You got it. That identlist on the end is the recursive call. It tells the parser to apply the same rule all over again. It's what lets you chain them together. X, comma, list, which becomes Y, comma, list, which becomes Z.
That's so clever. It's one finite rule that can generate an infinite number of possibilities.
It's incredibly elegant. And once you start thinking recursively, parsing trees and all this other stuff starts to make a lot more sense.
Speaking of that, let's talk about derivation. This is the process of actually using the rules to build a sentence.
Right. Derivation is how you prove that a line of code is valid. You start with highest level rule, the start symbol, and you just keep replacing the non-terminals.
The notes have this great example for A or B plus C. We'd start with something like a sign.
Yep. Then you look up the rule for a sign, which might be ed equals expr. So you swap that in.
Now you've got a mix of terminals and non-terminals. The notes mention leftmost derivation, which I guess just means you start with the one on the left.
That's all it means. So you would replace the leftmost non-terminal, id, with A. Now you have A equals expr. Then you replace expr.
And you just keep going down the line, replacing all the angle bracket things until you're left with nothing but terminals, and you have A equal B plus C.
You've done it. You've derived the sentence. And that whole process creates a structure, a tree. That's the parse tree. And it is what the compiler uses to understand the relationships in your code.
So if you build the tree wrong, you could mess up the order of operations or something.
Exactly. The shape of that tree is the logic of the expression.
This all ties directly into the actual work the students are doing. The notes call out specific assignments for the teams in the class.
Yeah, it's a divide and conquer approach. Team Best has to create the B and F for the while statement and for a whole class definition.
Oof. A class definition sounds hard. It's got methods, variable.
It's very recursive. You have structures inside of structures. Yeah. Then the drafts are on the hook for method definitions and method calls.
Also tricky. A method call can have, 0 arguments? A dozen?
Right. They'll need to use that recursive list trick we just talked about for the parameters.
The notes also show the classic Java if statement example, the whole dangling else problem.
A rite of passage for compiler writers. If you have an if inside another if, and only one else, which if does it belong to?
The inner one or the outer one?
Exactly. The B and F has to be written in a way that makes that completely unambiguous. The symbol gives you the choice, if with an else or if without. But the structure of the rule forces the compiler's hand.
It's clear the students are really engineering the language logic here, not just memorizing.
They absolutely are. And speaking of engineering, we should get into the nitty-gritty, the housekeeping stuff. There are some serious deadlines coming up.
Yes. Let's make sure everyone has this. First up, Monday, February 16th, Lab 2 is due.
That's the Flex Lab. And I really want to emphasize, it has both a team part and an individual part. Don't forget to submit your individual file.
We see that happen all the time. The team part is done, everyone's happy, and someone forgets their own submission.
And it's a 0. Don't let that be you.
Okay. Then on Wednesday, February 18th, you need to read Appendix B of the compiler's book.
This is to get you ready for Lab 3, the B minor scanner. The scanner is the piece that comes right before the parser we've been talking about. It turns raw text into tokens.
And for that reading, the notes are very specific about the 2-1 rule for perusal annotations.
This is not optional. It is a minimum of 2 paragraphs of annotation and a minimum of 1 quiz question that you create.
And by 2 paragraphs, they mean thoughtful commentary, not just, I agree.
Exactly. The syllabus calls it collaborative note-taking. The goal is to prove you engaged with the material, not just that you opened the page.
Also, a quick syllabus reminder about office hours. Dave Reed has them, and there's a scheduling tool. If you're stuck on recursion, that's the place to go.
And for the teams, Team Best, the giraffes, all of you, remember to rotate those leadership roles. Mm-hmm. Chief Understanding Leader, Chief Equity Leader.
I still want the title Chief Understanding Leader.
It's the most important job. That's the person who stops the meeting and says, wait, do we actually get this, or are we all just nodding? That person saves the grade.
Before we sign off, there's one last point at the end of the notes I wanted to touch on. It's a bit of a provocative thought.
Okay.
We just spent all this time talking about how B and F can generate syntactically perfect code, but the final note says there's little chance that a generated program or statement will work.
It brings us right back to the sandwich.
Yeah.
You can use B and F to generate a program that is 100% syntactically correct. All the brackets match, the semicolons are there, but if you try to run it,
it would just be gibberish.
Total garbage. It would do nothing useful or crash immediately. It's like that famous sentence from Chomsky, colorless green ideas sleep furiously. Grammatically, it's a perfect English sentence.
But it means absolutely nothing.
Exactly.
Yeah.
Syntax is the shape, but semantics is the meaning. And it leaves you with this big question. We have these perfect mathematical tools like B and F to solve the syntax problem. We've nailed it. But why is defining the meaning, the semantics, the logic, still so incredibly hard?
That is definitely something to chew on. The fact that we can build a perfect sentence and still say nothing of value.
It's a very human problem when you think about it.
Too true. All right, that's our deep dive for today. You've got your mission. Understand the difference between syntax and semantics, get your head around B and F and that recursion trick, and visualize the derivation tree.
You have your deadlines. Lab 2 is due Monday. Read Appendix B for Wednesday.
Good luck with that Flex Lab. Don't let your syntax get rejected. We will catch you in the next deep dive.
Happy coding.